All right, class, so this will be the last video that you have to watch for this Calculus 1 course. We are going to cover 3 sections because they're all relatively short, so we'll put them all together in one. We're going to do sections 3.5, 3.7, and 3.9 today. So first in section 3.5, I kind of want to just do kind of a summary of curve sketching. We're only going to look at a few problems in this section, but it's kind of a way that you can see one more time all the techniques of graphing. We hadn't sketched much of anything yet, so we're going to sketch some graphs today as well, along with finding everything we found in the last video. Before we do that, though, one small thing that I left off in the last section was a third kind of asymptote. So we are going to actually look at slant asymptotes today. So remember, we talked about horizontal and vertical asymptotes. Vertical we've been doing since chapter 1. We introduced horizontal asymptotes in the last video. That means you take the limit as x approaches infinity. Now we're going to look at slant asymptotes. And there's a formal definition for it, and it's given right here. Let me box that in for you. I don't use this formal definition very much, but it's there if you'd like to use it. So instead, here's kind of my little hint to you. For rational functions, you will have a slant asymptote when the degree of the numerator is exactly one more than the degree of the denominator. To find slant asymptotes, we are going to use long division. So for example, if you had something, I hope it's in the problem that I picked out, but what if you had something like x cubed plus 1 over x squared plus 1? Now in this instance, since the power on top is larger than the power on the bottom, it is not going to have a horizontal asymptote, and there's a reason why. You cannot have a horizontal and a slant asymptote both. You're going to have one or you're going to have the other. In this case, you're going to have a slant because the power on top is one larger. So we would do long division. I'm going to remind you how to do that in 1 second. And we are going to find what the slant asymptote is. Oh, good. It wasn't the same one. So example number 1, it's close. Example number 1, what is the slant asymptote of x squared plus 1 over x plus 1? So as you can see, the power on top is one larger than the power on the bottom. So as a reminder about long division, whatever is on top, that is what goes inside of your divisor, or some people call it the house. And then on the outside is the bottom, which is x plus 1. And essentially your goal is to try to cancel these terms inside of the divisor. So to get rid of that x squared, you have to ask yourself, what am I multiplying x by to get rid of it? Well, we should all know that x times x is x squared. So I'm going to take the x and multiply it by 1, or x plus 1. So x times x is x squared. X times 1 is x. And remember back in 3rd grade when you did division, you subtract what you got when you multiplied. Now every time you do this, since you're picking the number, you should always be able to cancel the first term, but everything else you have to simplify. There's not an x inside the divisor, so that's understood to be 0x. So 0x minus this x would be negative x, and then this plus 1 you can just bring down. Do it again. You can now say, okay, I want to get rid of negative x. What times x makes it negative x? Well, that would be minus 1. So negative 1 times x is negative x. Negative 1 times positive 1 is negative 1. And once again, if you subtract these, you should always be able to cancel the first terms. That's the whole point. And then 1 minus a negative 1 gives you a 2. Now, once this becomes just a constant, you're done. You don't have to do anything else. The part in blue is your slant asymptote. So in this example, your slant asymptote would be y equals, not what I just wrote down. Do not do that. It would be y equals x minus 1. And you're done. No horizontal, so you can't have both. So there's no way to have all 3 kinds. If you have a horizontal, you can't have a slope. I'm sorry, a slant. If you have a slant, you cannot have a horizontal. Let's look at a second one. And like I said, after this one, we're going to move on to something else. These aren't very popular, but I want you to be able to see it in case it ever shows up another topic you have to cover. What if you're given 4x cubed minus 10x squared minus 11x plus 1 over x squared minus 3x? So as you can see, the power on top, which is cubed, is 1 larger than the power on the bottom, which is squared. So we can do long division to find the slant asymptote. So we're going to have 4x cubed minus 10x squared minus 11x plus 1, and we're going to divide that by the x squared minus 3x. So going through the same process, what times x squared will make it a 4x cubed? Well, that would be 4x. So that would give us, so 4x times x squared is 4x cubed. 4x times negative 3x is negative 12x squared. And remember, you're subtracting these two. So when I do that, you should end up with canceling the 4x cubes, and then negative 10x squared minus a negative 12x squared means you're going to add them, and you get 2x squared. And then you can bring down your other terms, the minus 11x and the plus 1. All right, now get rid of the 2x squared. The 2x squared should go away if you multiply x squared by just a 2. So you're going to have plus 2. 2 times x squared is 2x squared. 2 times negative 3x is negative 6x. Subtract both of those, and just like I wanted to, the x squared terms go away. Negative 11x minus a negative 6x means you're going to add them, and you have a negative 5x, and you bring down the plus 1. Now, I misspoke on the last slide. I said you're trying to go down to the constant. That's not true. You're just trying to go until the term that you have left over is less than what you're trying to divide. So x is less than x squared, so you don't need to divide anymore. That part in red up there is your answer. So the slant asymptote of this problem is y equals 4x plus 2. All right, so to move on to a bigger part of this section. So these problems will take a few minutes because there's a lot of things we got to do. So guidelines for sketching a curve. Now some of these, and these are the 8 that are in your textbook, some of these we're not going to do, so I'm not too much worried about them, but I'm going to read through them and we'll talk about what we need to worry about. So just to save you a little bit of time, don't worry about number 1 because number 1 can be done in number 4, so don't worry about that. And then honestly, number 3, I'm not too much worried about symmetry. We can talk about it along the way, but I'm not going to put a lot of stock into that. The other 6, though, are what I'm looking for you to do. Find the intercepts. We saw how that was helpful in the last section when we did the one with the asymptotes. So we'll find intercepts. We will then find our asymptotes because if you can plot an asymptote on there, that helps you get a guide. Then we're going to move to all the derivative stuff. Increasing and decreasing intervals, that's from the first derivative. Local extrema, that's the local max and local mins we discussed last time. Then we're going to do the intervals of concave up and concave down along with the inflection points. And then the new thing today, number 8, we're then going to use all this information to sketch a graph of the function. So we're going to do 3 of these. So starting off with number 2, part A. If you're given y equals x cubed plus 3x squared, can you find all that information I discussed, and then we will use that to help us sketch a graph. So kind of going in the order that was listed, number 1 is find your intercepts. So like we did in the last video, I'm going to start off with my x-intercept, which means I need to let y be 0. So 0 equals x cubed plus 3x squared. That does factor by taking an x squared out of both terms. I can set both of those equal to 0. And when you solve both of them, you should get x equals 0 and x equals negative 3. So this graph is going to cross or touch the x-axis at least twice. Then we're going to do the y-intercept. So right next to it, this one's always the easier one to do. Y-intercept means x is 0. So that would be y equals 0 cubed plus 3 times 0 squared, which all that just goes away and becomes y equals 0. Okay, so there's your intercepts. Then we're going to move on to your asymptotes. Now keep in mind, just because asymptotes is what we've talked about does not mean we're going to always do them. As you can see, there are no fractions in this problem. There's also no square roots, which we saw an issue with last time. So if there's no fractions and no square roots to cause problems, we can just say the asymptotes are none. There's not any, so we're not going to draw any asymptotes in this problem. Then we get to the first derivative stuff. So we're going to find out where is it increasing, where is it decreasing, and where are your local maxes and mins. To do all of that, we must first find our derivative. So this is not f, let's call it y prime to keep it consistent. So we're going to call this y prime is equal to 3x squared plus 6x, and to find those critical numbers, I'm going to set that equal to 0. They both share a 3x in common, so I'll factor that out to leave an x plus 2 left over. I can then set both of those factors equal to 0. So 3x equals 0, x plus 2 equals 0, and you get two critical numbers, 0 and negative 2. Remember, these critical numbers are what divides up your intervals of increasing and decreasing. So I'm going to plot both of them on a number line in order. So make sure you always put them in order. And then pick out your test values. This would be negative 3. Let's do negative 1 and 1. Remember, these are getting plugged into the first derivative. It doesn't matter whether you use the factored or the unfactored form. I just prefer to use the factored form most of the time. And I'm going to plug these three numbers in and see whether or not I get a positive or negative number. So if you plug negative 3 in, that's going to be a negative 9. That's going to be a negative 1. So multiplying that together makes it positive. Plugging negative 1 in, that's going to be negative 3 and positive 1. So you should get a negative number. And then plugging 1 in, you should get a positive number. So we can answer, I'll answer the first two parts down here. The intervals of increasing are the positive intervals, so that would be negative infinity to negative 2, union 0 to infinity. Then you have the intervals of decreasing, that's just the negative part, so that's in the middle. That is from negative 2 to 0. I don't want to cram it all down here at the bottom, so well, actually we'll just go right next to it. So the next two questions are there any local maximums or local mins? All right, so the local max in this case is going to occur when you go from increasing to decreasing. So that's going to occur at the negative 2. We'll find the y value in a second. The local min is when you go from decreasing to increasing, so that's going to occur at the 0. So that's going to end up being 0, and then we'll find the y value. To get both of these y values, you plug them back into the original problem. So if I plug the negative 2 in, let's see, that's going to be negative 8 plus 12, so that's going to be a 4. And if you plug 0 in, you actually get 0. So you have one local minimum and you have one local maximum. All right, so let's go back to red. I'm going to kind of box all this stuff off. Like I said, this is a lot of stuff. Now we're going to move on to the second derivative stuff, which is going to be your intervals of concavity and your inflection points. So I need y double prime. So go back to your first derivative and take the derivative again. That will be 6x plus 6 that I'm going to set equal to 0. Subtract the 6 over, 6x equals negative 6, and then dividing by 6 gives me x equals negative 1. Only one number, so we're going to put it right on the number line, so right in the middle. And then picking out a couple of test values, how about negative 2 and 0? Remember, plug these numbers into the second derivative, so that's the 6x plus 6, and that would be negative 12 plus 6 is a negative number. And then 6 times 0 plus 6 is a positive number. I can now say that this function is concave up on the positive part, so that's from negative 1 to infinity, and you are concave down on the negative part, which is negative infinity to negative 1. You have inflection points whenever you switch, which we have one spot. So at x equals negative 1, it does switch. This is a point now. So to find the y value of this point, plug the negative 1 back into the original function. So that's going to be, let's see, negative 1 plus 3 is positive 2. And you have your intervals of concave up, concave down, and your inflection points. All right, and then last but not least, we are going to put all of this together to draw one big graph. So what I usually do first is I go through and I plot all the points that I found. So starting back up here in the intercepts at x equals 0, which is right at the origin, and x equals -3, I know we have x-intercepts. The y-intercept we already did because y equals 0 and x equals 0 both occur at the same spot, which is the origin. We have a local max and a local min, so the local max occurs at -2, 4. So I'm going to go left 2 and up 4 to get my local max. And the local min, we've actually already plotted as well because it's right there at the origin. You have the inflection point, which is -1, 2. So left 1, up 2. So we have our inflection point. And then I usually just use the intervals of increasing and decreasing to draw the rest of this. According to this bottom left intervals, you should be increasing all the way until you get to x is -2, also known as your local max. So I increased going through my intercepts. Then I decrease down to my local min, which is at 0, 0. And then after 0, it says that I increase everywhere else. And that is a rough sketch of your graph. Not looking for perfection or anything. I know on the computer usually it's a lot better, but this is a rough sketch of what x cubed plus 3x squared looks like using our ideas of calculus. All right, that was so much fun. We're going to do it again. So looking at part B, we've got y equals x to the 4th minus 4x. And I'm going to go through the exact same process again, not changing it up because I don't want to lose anybody. So first thing are the intercepts. So I'm going to begin by finding my x-intercepts. So once again, remember that is y equals 0. All right, so if I do that, that is 0 equals x to the 4th minus 4x. They both share an x in common, so I'll factor that out and make it x cubed minus 4. And if I set both of those equal to 0, it's x equals 0 and x cubed minus 4 equals 0. The one on the right, you can do x cubed equals 4. And then not a pretty number, but that's okay. We can say that x occurs at the cube root of 4. So we've got two different x-intercepts. For your y-intercepts, always the easier one, let x be 0. So that's going to be y equals 0 to the 4th minus 4 times 0. And since we already kind of knew this, but I went ahead and worked it out, we also have a y-intercept of 0. Similar to the last one, there are no fractions, there are no square roots to worry about. So as far as the asymptotes go, there are none again. So we're not going to draw any asymptotes on this problem. All right, so now to your calculus part. I need the first derivative. So y prime is going to equal 4x cubed minus 4, and I'm going to set that equal to 0 to find the critical numbers. I'm going to add the 4 over, so 4x cubed equals 4. I'm going to divide by 4, which is x cubed equals 1, and then the cube root of 1 is going to be just 1. It's not plus and minus because there's no even root here. So in this case, you are going to make your number line. And since 1 is our only critical number, that's the only number I'm going to plot there. So we've got 0 and 2. I'll pick those as my test values. And remember, you're plugging these into your first derivative to check for increasing and decreasing. If you plug 0 in, you will get a negative number. While if you plug in 2, you're going to get a positive number. So I can say that the interval of increasing is from 1 to infinity, while the interval of decreasing is from -infinity to 1. You only have one critical number here, so it goes from decreasing to increasing. So while you do not have a local max in this problem, you will have a local minimum at x equals 1. Take that 1 and plug it back into the original function to get the y value. So if you plug 1 back in the original, looks like you should get a -3. And then I'll go ahead and jot it down here in case you're looking back at this video later. Your local max is going to be none. There's just not one in this particular function. So that takes care of all the first derivative information. Let's move on to the second derivative. So we're going to find where is it concave up and where is it concave down, along with the inflection points. So first thing I got to do is I got to find y double prime. So take your derivative of the derivative. So the derivative of 4x cubed is going to be 12x squared, and the minus 4 does go to 0. Set this whole thing equal to 0 and do a little algebra. Dividing by 12 will give you x squared is 0, and then taking the square root of both sides still keeps you with a 0. Okay, that's nice. Again, only one number. I'm going to plot the 0 right in the middle, and then I am going to pick test values of -1 and let's say +1. But here's where the trick comes in. When you plug both of those numbers into the second derivative, which is just 12x squared, you're going to always get a positive number. So you actually end up getting pluses on both sides. So how do we note that for our homework? Well, since they're all plus, that means you are actually concave up everywhere. Your graph is never going to be concave down. And then since the interval of concavity did not switch, it went plus plus, that also means you do not have an inflection point. So not really a lot you learned about the second derivative. So what does that mean the graph's going to look like? So let's see. I'm going to draw my x and y axis, but let's plot the points that we can. We have some intercepts. We have an x-intercept of 0, and we also have an x-intercept of the cube root of 4. So let me get what approximately, excuse me. So the cube root of 4 is about 1.58, so we'll mark that accordingly. So it's going to be about, let's call it 1.5-ish. So there's our intercepts. You have no asymptotes, and you only picked up a local minimum. So if I go to 1, -3, there's my local min. Now here's where the trick comes in. You must keep your graph concave up at all times, but you have to change your interval of increasing and decreasing. So we are going to decrease from the beginning all the way until you get to your minimum. But what ends up happening is it looks something like this. So you're concave up, you hit this point, and then you kind of fake yourself out a little bit. So it looks something like this. I missed my point, but that's okay. We'll make it bigger. So you have a graph that has that 0 up here in the red part with the second derivative. We thought that was going to be an inflection point, but it ended up not being. What did happen, though, is while you did stay concave up, the level of concavity did change. So it's not the exact same. It's not a parabola, so please don't draw a parabola here. You have to take into account that at 0, something is happening because there's a reason that our second derivative did equal 0. So while it's not a perfect graph right there, that is going to be your rough sketch. All right, so like I said, decide just to leave off part C there because we, like I said, didn't want to do that one there. But in this case, we're now going to move on to the next section, which is optimization. So in the optimization section, we are going to look at more word problems. Now, these are not like the related rate problems, so that's good news. There's no rates of change. Instead, we're going to use word problems to solve using maximums and minimums. So how does max and mins help us solve, in this case, word problems? So there's not really anything new here. I'm going to kind of show you a few things along the way, but here's our first idea. This is an example of an optimization problem. It says find the dimensions of a rectangle with a perimeter of 132 meters whose area is as large as possible. So on a lot of these problems, kind of like in the related rates section, I'm going to try to draw a picture to kind of label things for you. Essentially, you have a rectangle, and you know that the perimeter has to be, 132 meters. We're trying to figure out the area needs to be maximized. Can you find the largest area possible? Okay, so what do we know here? Well, we probably remember from when we did basic geometry is that if you call your widths x and you call your lengths y, we could find the perimeter of a rectangle by doing 2x plus 2y, but according to the information, I know that the perimeter has to be 132. So 132 has to equal 2x plus 2y. What about the area? from geometry, the area of a rectangle is length times width, but according to our variables, that's going to be x times y. Since we are trying to maximize the area, I need to take the derivative of a, but I don't have any rates of change, so we're not going to do related rates here. Instead, we have to do a substitution technique. I need to get rid of this y in the area formula. Easiest way to do that is I'm going to solve for this y in the perimeter formula. So let's come down here below. Since we know 132 has to equal 2x plus 2y, get that y by itself. Subtract the 2x over. 132 minus 2x equals 2y. And then if you divide everything by 2, you should get 66 minus x is y. I'm going to take this 66 minus x and I'm going to plug it into that y in the area formula. So area is x times 66 minus x, and if I multiply that x through, it is 66x minus x squared. That is now something that's a lot easier to maximize. So to find maximization, we need the critical number. So at this point, the last thing you got to do is take the derivative of a, which is 66 minus 2x, and to make it a critical number, we're going to set that equal to 0. I'm going to move the 66 over, so negative 2x equals negative 66, and then dividing both sides by negative 2, x equals 33. All right, you've got the x. Now you got to find the y because you need the dimensions. So once you have the 33, you can now plug that back into your formula for y and get the length. So in this case, 66 minus 33 is also 33. So both your length and your width have to be the exact same number for the area to be as large as possible. And that's kind of the idea we're going to look in this section, is that given information, can you write a few formulas so that you can maximize, and we'll see some minimize, certain properties. All right, so let's look at another one. In this case, if 1,200 squared centimeters of material is available to make a box with a square base and an open top, find the largest possible volume of this box. So essentially, I'm going to add some dotted lines so we can kind of see the inside of the box here for visualization. You have this box, or this cube, that has an open top, and I know that you can only use 1,200 squared centimeters of material. What is the volume of this box that's the largest as possible? All right, well, first thing I notice is that they gave us the 1,200. So that is going to be the surface area. So you've got to figure out the area of this box. Now it did say that the bottom is a square base. So if I know that both the bottom dimensions are the same, let's just call them both x, to find the area of the bottom, it's got to be x squared. And then since it has 4 walls on the outside, I know I'm going to have to add to this 4 times the area of each side. But it didn't say that you had to have a square side, so I can't call the height x here. We have to assume that it could be something different. Let's say y. So the area of each of these 4 sides of the box would be x times y. So there's your surface area formula. We're trying to maximize the volume, so I need the volume of this box, which is typically length times width times height, but in this case it's x by y, which we can write as x squared y. Very similar to the last problem we did. The problem is that you need this y in volume to go away. So that means we're going to solve for the y in the surface area formula. So that means that I can say that 1,200, if I move the x squared over, make it minus 1,200, I don't know why I flip-flop the variables, but that's okay. 1,200 minus x squared is equal to 4yx. Then to get the y by itself, divide everything by 4x. And while it's not pretty, this is your formula for y. Substitute that into your volume formula. So volume is now going to equal x squared times 1,200 minus x squared over 4x. First thing I notice is that I can cancel the x on the bottom with one of the x's out front, so that's just x to the first. And then if I distribute that x to the first through, you should get 1200x minus x cubed, all being divided by just a singular 4. And now I can divide the 4 into both of those terms. This would end up being 300x minus 1/4 x cubed. That volume formula now only has x's in it, so now you can maximize the volume. So we're going to find v prime, so take the derivative. That would be 300 minus 3/4 x squared, and to find its critical number, we're going to set that derivative equal to 0. Oh, let's see, I'm going to move the 300 over. So that is negative 3/4 x squared equals negative 300. I am now going to multiply everything by negative 4/3 on both sides, because what I'm trying to do is the negative 4/3 and the negative 3/4 cancels each other. And then if I do negative 300 times negative 4/3, you should get a 400. And then taking the square root of both sides would be typically plus or minus 20, but you only have to do the positive 20 because length in your problem cannot be negative. So we'll just call x is 20. So that gives us the base of this box, so 20 by 20. I now need the height of this box, which is y. So I'm going to plug x into my y formula. That is 1200 minus 20 squared over 4 times 20 equals y. So that should give us 1200 minus 400 over 80 equals y. And then doing a little bit of number crunching there, you should get your y value to be 10. Now, normally you would be done, but it actually asks us to find the largest possible volume. So way back up here at the top, you have your volume formula. Plug in the x and y you just found. Volume would be 20 squared times 10. So that is 400 times 10, which is 4,000. And we have to call this cubic centimeters. This is the largest possible volume you can find of this box according to the parameters that we were given. All right, so example number 3. Find the point or points on the ellipse 4x squared plus y squared equals 4 that is or are farthest away from the point 1, 0. All right, so the biggest difference here is that it's a formula you're going to have to remember from algebra. It's talking about distance. So back in algebra, and I'm going to write it up here in case you don't remember, the distance formula from a point to a point, because we're trying to find, we have one point, we're trying to find another point, was the square root of x2 minus x1 squared, that is horrible handwriting, there we go, plus y2 minus y1 squared. Your job is, in order to use this formula, you're going to have to find an x1, y1 and an x2, y2. Now, one of those points is already given to you. It's given to you as 1, 0. The second point, since we don't know exactly where it's at, we can't use numbers. We will have to use representations of each part. Now, the x, I have no problems with. We want everything to be x's, so I'm actually going to call x2 just x because we'll find it later. I cannot leave y2 as y. I now have to take the original problem, which was 4x squared plus y squared equals 4, and I need you to get that y by itself. So if I subtract the 4x squared over, y squared is going to equal 4 minus 4x squared. And then if you take the square root of both sides, you're going to end up getting plus or minus the square root of 4 minus 4x squared. And like I said, just leave it like that. But you do have to do the plus and minus because there could be multiple different points. We have to include every case. So plugging that back in, we will call this plus or minus the square root of 4 minus 4x squared. I am now going to take these four numbers, or four functions, or four parts, and plug them into my distance formula. So I can say that distance is equal to the square root of x2 minus x1, so that would be x minus 1 all squared, plus y2, which is plus or minus the square root of 4 minus 4x squared minus 0 all squared. So multiplying all of that out inside of your square root, if you FOIL the x minus 1 by itself, you should get x squared minus 2x plus 1. And then the good thing about subtracting 0 is it doesn't change anything. And the good thing about squaring a square root is you should just pick up a plus 4 minus 4x squared. The extra square root will cancel. I'm going to combine my like terms here. So you should get, looks like a negative 3x squared, a minus 2x, and then also a plus 5. Now I got to take the derivative of this in order to maximize the distance here. So I'm going to rewrite this in an easier way so I can take the derivative. So I'm going to raise the entire function to the 1/2 power. Excuse me. And now I'm going to take the derivative by doing the chain rule. So that would be 1/2 times, leave the inside alone, subtract 1 from the power down to the negative 1/2, and then multiply by the derivative of the inside, which is negative 6x minus 2. Multiply the 1/2 by that part, so that would be a negative 3x minus 1 is going to, not equal, sorry, multiplied by that whole stuff. So multiplied by negative 3x squared minus 2x plus 5 raised to the negative 1/2. And then if I rewrite this in a nice cleaner way, it would be negative 3x minus 1 over negative 3x squared minus 2x plus 5 raised to the 1/2 power. So now you need to set this derivative equal to 0 in order to form the critical number so that it maximizes. The good thing about a fraction, though, is that a fraction will only be 0 when the numerator is 0. So I'm going to take negative 3x minus 1 and set that equal to 0. I'm not worried about the bottom because the bottom being 0 is not going to help me maximize anything. So add the 1 from both sides. That's negative 3x equals 1. And then dividing both sides by negative 3, x is negative 1/3. But here's why you can get more than 1 point. When you plug negative 1/3 back into the original y function, you actually get two different y values because of the plus or minus. You actually get y equals plus or minus the square root of 4 minus 4 times negative 1/3 squared, which is plus or minus the square root of 4 minus 4 times 1/9, which is plus or minus the square root of 4 minus 4/9, which is equal to plus or minus the square root of, you should get a 32/9, which is equal to plus or minus the square root of 32 over 3. And then you can break down the square root of 32 into 4 square roots of 2 over 3. Same x value, two different y values, so therefore the 2 points that form the furthest distance away are going to be negative 1/3, positive 4 root 2 over 3, and negative 1/3, negative 4 root 2 over 3. You have two different points of equal furthest distance away. All right, one of my favorite problems in this section, the pizza problem, because I'm always hungry. So if you are offered one slice from a round pizza, in other words, a sector of a circle, and the slice must have a perimeter of 32 inches, what diameter pizza will reward you with the largest slice? All right, so in this case, we are going to focus on this pizza slice. So this little piece right here. What do we know about this pizza slice? Well, we know that this part right here would have to be the radius, and that's going to be the same thing on both sides. We also know that the outside crust is a formula that you probably saw in trig that we're going to review called arc length. We call that S. So let's use this to kind of fill in the gaps here. The slice of pizza must have a perimeter of 32 inches. So around this pizza slice has to add up to 32. So I know that 32 is going to equal 2 times the radius plus the arc length. Now, do we remember what the arc length formula is? Well, the answer is that S is equal to R times theta. So I can actually say that 32 is equal to 2R plus R times theta. All right, I need another relationship here. The problem is the theta. So is there another formula using circles and arc length that might come in handy? Well, the answer is area. The area of this piece of pizza right here can be found by doing 1/2 R squared theta. Now, this is what we're trying to maximize here. We're trying to maximize the area of this piece of pizza, and then we'll use that to help us find the diameter. So the problem is that I need to get it all in one letter. So I would probably get it all into theta. So I'm going to get the theta by itself in the first formula. So down here, I'm going to take the 32 equals 2R plus R theta. I'm going to subtract the 2R over. So 32 minus 2R equals R theta. And then dividing everything by R means 32 minus 2R over R is equal to theta. Plug this theta into your area formula. So area equals 1/2 R squared times 32 minus 2R all over R. Very nicely, at least the fraction goes away because this R cancels one of these R's off. And if I multiply all of this out, I can say that area is equal, so 1/2 R times 32 is 16R minus 1/2 R times negative 2R is minus R squared. Take the derivative. A prime equals 16 minus 2R equals 0. Move the 16 over, so negative 2R equals negative 16, and therefore R equals 8. But make sure you read the question. It asks for what does the diameter have to be of the whole pizza. So if the radius of this slice is 8, we're going to double that, and we can say that the diameter of this pizza needs to be 16 inches in order for us to maximize the area of this piece of pizza that has a perimeter of 32 inches. All right, to wrap up this section, got a couple of farming problems I want to do, and you'll see what I mean when I do these. So the first one says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders his barn. He needs no fencing against the barn. What are the dimensions of the field that has the largest area? So it's kind of hard to see from this picture, so I'm going to kind of redraw this a little bit. Let's assume that, and I'm going to do it from a kind of a sky view. You have the barn, and then you have this, what do they call, oops, I missed for make the barn a little bit bigger. We have this rectangular field attached to the barn. So we're trying to know, you have 2,400 feet of fencing. Now it does say that you do not need any fencing on the side of the barn. So kind of like the earlier rectangle problem we saw, I'm going to let the widths be X, but I only have one length because I don't need fencing over there. I know I have to use 2,400 feet of fencing. So the 2,400 has to be what happens when you take both of your X's and your one Y and add them all together. So 2,400 has to equal 2X plus Y. All right, we're trying to maximize the area. So our area is going to equal length times width again. So the area of this rectangular field is X times Y. And it's going to work very similar to that very first problem we did. I need to get the Y by itself. So I'm going to subtract the 2X from both sides. That's easy enough. Plug this into my area formula. So area is x times 2400 minus 2x. So area is 2400x minus 2x squared. To maximize this, I'm going to take the derivative and find a prime, which is 2400 minus 4x, and I'm going to set this equal to 0. Moving the 2400 over to the other side, I can say that negative 4x is equal to negative 2400, and then dividing both sides by negative 4 should give you an x dimension of 600. Since it also needs the length, I'm now going to plug this back into y, and I can say that 2400 minus 2 times 600 equals y. So I can say that the length of this rectangle has to be 1200. And that's it. So it's just making sure you read the problem, because if you had put fencing on the barn side, you would have gotten the wrong dimensions of this rectangle. So make sure you always read every question in this section. So let me do a different, what I call farming problem, is instead of me giving you the dimensions, giving you the perimeter, why don't I give you area and ask for the same idea? So what about one like this? A farmer has a 5,000 square foot area that he wants to fence. The area is going to be separated into 3 pens for different animals, as in the diagram below. What are the dimensions of the field that will minimize the cost of fencing materials? So you'll see here is that normally you just have a length and a width, but now while you still have the widths of x, and then this whole thing here is going to be your length of y. So there's no barn this time, so everything gets it. You have to now add in 2 extra x sections, or cross sections as some books call it, because you have to then divide up the different kinds of animals. So that's going to have to go into part of your fencing. So making sure you minimize your cost. So what do we know? We know that this entire area has to be 5,000 square feet. Now, the extra x's have nothing to do with the area. The total area of this rectangle is still length times width, which is x times y. But we're trying to now figure out the perimeter. So what perimeter can we do to minimize the cost of fencing? So add up all your variables. I know that we have 2 lengths, which is 2y, and you have to actually use 4 widths because of the cross section. So perimeter will be 2y plus 4x. The problem is that I can't maximize this until that y goes away. So in my area formula, to get y by itself, I'm going to divide both sides by x. So 5,000 divided by x is y, and I'm going to plug that into my perimeter formula. Perimeter would be 2 times 5,000 over x plus 4x. Putting that together is going to make the perimeter equal to 10,000 over x plus 4x. And this is what I want to take the derivative of. Now it's going to be easier if you go ahead and rewrite that first term right there. So I can say that perimeter is 10,000 x to the negative 1 plus 4x, because I'd rather do the power rule here if possible. So therefore P prime is going to be negative 10,000 x to the negative 2 plus 4, and this now needs to equal 0. Now that my derivative's done, I'm going to put it back into its original format. So this is negative 10,000 over x squared plus 4 is 0. I don't like the fraction, so I'm going to multiply everything by x squared, which is going to give me a negative 10,000. That x squared cancels. X squared times 4 is 4x squared, and then 0 times x squared is still 0. I'm going to move the 10,000 to the other side. So 4x squared has to equal 10,000. Divide by 4. So x squared has to equal 2,500, and then the square root of 2,500 is 50. So all of those widths, all 4 of them, have to equal 50, in this case, feet. And then way back up here, We can now find our y value by plugging this into our y formula. So y is equal to 5,000 over 50. So y is going to equal 100. And you have now found the dimensions of this rectangle that will minimize the cost of fencing materials of this 5,000 square foot area. Very good. So that wraps up section 3.7, which is optimization. And for the last section in this class, we are going to do section 3.9, which is anti-differentiation. So in this section, if you are going on to Calculus 2 next, this section is very, very important because the idea of antiderivatives plays a big role in what the Calculus 2 class here offers. So while we're not going to do a lot in this section, I do want to kind of show everybody the basics, especially for those who are not going, for those who are going on to Cal 2. If you're not going on to Cal 2 next, well, this is kind of an extra section for you, but you still got to learn it for your final exam. So let me kind of show you the idea of where antiderivatives come from. Let's assume we have two different functions. We have f of x is x squared minus 7 and g of x is x squared plus 5. So far throughout this class, we've been talking about derivatives. Well, here's the problem. If you take the derivative of both of these, you're going to notice that both of them give you a derivative of 2x. But if you think backwards, they both did not come from the same function. The difference is that no matter what the constant was, the constant derivative went away. So when you're going backwards, which we're going to do antiderivatives, is how do you go from a derivative back to its original function? The problem is that since we don't always have enough information to know what that constant is, you're going to have to add a general term in, and that's this big theorem down here at the bottom. If you find the antiderivative of a function, you must add an arbitrary constant that we're going to call c to the end of every single one. Now, if I give you more information, maybe we can solve for that c, but every time, even if you have the information, when you take the antiderivative, you need to take and add a plus c onto the end of your answer. And you're going to see that throughout the rest of this section that I teach y'all. But the big rule is, well, how do you do an antiderivative? We know we're going to add plus c, but what do you do before that? So most of these rules you're going to learn, I say for Cal 2. The only rule that I really want to cover is the basic one. If you want to find the antiderivative of x to the n. Now we learned how to take the derivative of that by doing the power rule. If you want to do the opposite direction, you have to do everything opposite. Instead of subtracting 1 from the power, you are now going to add 1 to the power, so it becomes x to the n plus 1. And instead of multiplying by the power, you now have to divide by this power. So all in all, when you find an antiderivative of x to the n, you're going to raise the power up by 1, and then you're going to divide that term by whatever the new power is. So let's look at some examples of what I mean by that. So the first one, f of x equals 4x plus 7. If you want to find capital F of x, which is the antiderivative, so the 4 stays the same, instead of x to the first, you would add, sorry, I messed up there, you would add 1 to the power. So instead of x to the first, that now becomes x squared, and you're going to divide by that new power, which is 2. And we'll simplify everything in a second. When it's just a constant, kind of like when you took the derivative of, let's say, 5x earlier, it became 5. So if you're given just a constant, all you have to do to find its antiderivative is just add an x onto it. And then don't forget, there could be a constant there, so we have to also include plus c. Now after this step, I'm going to go through and simplify what I can. It's not much, but you should get a final answer of 2x squared plus 7x plus c. This is your antiderivative. And remember, you can always check yourself. If you take the derivative of this function, so the derivative of 2x squared is 4x, the derivative of 7x is 7, and the derivative of a constant is 0, so we can always verify our answers. So let's continue on. What if you have fraction exponents? So f of x equals 7x to the 2/5 plus 8x to the negative 4/5. When I find the antiderivative of this function, so I'm going to leave the 7 alone, I'm going to add 1 to the power. So 2/5 plus 1 is 7/5, and I'm going to also divide this by 7/5. Plus 8, add 1 to the power. Instead of -4/5, if you add 1, you get a positive 1/5, and then you divide that by a 1/5. Don't forget also your plus c. So what you probably remember from algebra is that instead of dividing by a fraction, it's easier to multiply by the reciprocal. So I can rewrite this as 7 times. I'm not going to divide by 7/5. I'm going to instead multiply by 5/7, x to the 7/5 plus 8, and then times, instead of dividing by 1/5, I'm going to multiply by 5/1. I apologize, my pen is starting to mess up a little bit. There we go, plus, and then you have x to the 1/5 plus c. Very nicely on the first one, your 7s just cancel, and you're left with a 5x to the 7/5 plus 8 times 5 is 40, x to the 1/5 plus c. That is your antiderivative. So the big thing here is add 1 to the power and then divide by whatever your new power is. All right, what if you have to do it twice? So what if I give you the second derivative of a function and ask you to get back to the original function the best you can? So we've got f double prime of x is 20x cubed minus 12x squared plus 6x. You can't just jump from the second derivative to the original, so we have to go one by one. Step 1, you got to find f prime of x. So take the antiderivative of all of this. This would be 20 times x to the 4th over 4 minus 12 times x cubed over 3 plus 6 times x squared over 2 plus c. Simplify where you can. 20 divided by 4 makes this 5x to the 4th minus 12 divided by 3 is 4x cubed, and then 6 divided by 2 is 3x squared plus c. This is the first derivative. But now you've got to do it again. So do the exact same thing, find your antiderivative again. So this time f of x is going to equal 5 times, add 1 to the power again and divide, so x to the 5th over 5 minus 4 times x to the 4th over 4 plus 3 times x to the 3rd over 3. Since c is a constant, you can do the antiderivative of that. So kind of like the 7 we saw on the last slide, it would just be cx, because we don't know what c is. And then you've got to pick up another constant that I'm just going to go to the next letter and call that d. Simplifying what you can, you actually have a lot of canceling here. 5 over 5, 4 over 4, and 3 over 3 all cancel, and you are left with an x to the 5th minus x to the 4th plus x cubed plus cx plus d. So based on the second derivative given to us, this is the most general original function that we can write. We don't have enough information to solve for c and d on this problem, so we'll leave the answer as it is. All right, so for the first time, let me show you an example of where you can actually solve for these constants. So here's our first one. Find the antiderivative f of little f that satisfies the given condition. So little f of x is 5x to the 4th minus 2x to the 5th, and capital F of 0 is equal to 4. Now, don't worry about that extra term yet. We'll get to that in a second. Work this like we've done the last 2 or 3 problems. We're going to find capital F of x by doing the antiderivative. So that is 5 times x to the 5th over 5 minus 2 times x to the 6th over 6 plus c, which does simplify into x to the 5th minus 1/3 x to the 6th plus c. That's normally where we would stop, but since I know this initial condition, we have to solve for C now. Capital F of 0. Hey, I know what capital F of x is, so why don't I take capital F of 0, and we're going to replace every x in our antiderivative with a 0. The good thing about that is that it becomes 0 to the 5th minus 1/3 times 0 to the 6th plus c, and since the zeros just go away, you're left with a c. Now, this term you found, this c, now has to equal whatever the number is given in the problem, which in this case is 4. So I know that c is 4. I can now take that 4 and put it back into my antiderivative. So you can say that capital F of x is equal to x to the 5th minus 1/3 x to the 6th plus our new constant 4. And that is how you solve for C using antiderivatives. All right, let's do another one. What if I tell you a particle is moving with the given data? Find the position of the particle. So we know that A of t is t squared minus 4t plus 6, and S of 0 is 0, and S of 1 is 20. All right, so in this case, we're trying to go backwards. So normally we start position and we say the derivative of position is velocity, the derivative of velocity is acceleration. Now we're going to go backwards. To go from acceleration, if you take the antiderivative of that, you get a velocity function. So doing the velocity function, you should get t cubed over 3 minus 4 times t squared over 2 plus 6t plus c, which does simplify into 1/3 t cubed minus 2t squared plus 6t plus c. Now, neither one of these initial conditions has anything to do with velocity, so we can't solve for c yet. We're going to have to continue on and find position. So I'm going to find the antiderivative again. To go from v, the antiderivative of that would be s. So that's going to end up being 1/3 times t to the 4th over 4 minus 2 times t to the 3rd over 3 plus 6 times t squared over 2 plus ct plus d, which does simplify into 1/12 t to the 4th minus 2/3 t cubed plus 3 t squared plus ct plus d. Now, while this will end up being your answer in the end, you've got to figure out what c and d are in order to give me a complete answer. So I usually go with the easier numbers first. In that case, is s of 0. So if I do s of 0, that means in that little reddish box I have there, all of these t's have to go to 0. And if you let all of them go to 0, they all go away, and the only thing left over is the constant d. Now this constant d has to now equal the number that's by itself, which is 0. That's actually the best case scenario. That means actually this value of d is not there. There is no constant on the very end. But now that the d is gone, we can now solve for the c using our second condition. We can do s of 1. So if I plug 1 into all of these parts, the ones don't really change the value, but you do have all the constants. So it would be 1/12 minus 2/3 plus 3 plus c. This has to equal the constant in the initial condition, which is 20. So finding some common denominators here, looks like you're going to have a 1/12 minus an 8/12 plus a 36/12 plus c is 20. Putting all of those together, let's see, -7, that's going to be 29 over 12 plus c is 20. And subtracting that over, you should say that c is equal to, let's see, 240 over 12 minus 29/12, which is equal to 211 over 12. That's going to get plugged in for C, and you can now write your final answer. S of t is equal to 1/12 t to the fourth minus 2/3 t cubed plus 3t squared plus 211 over 12 t. Remember, the value of d went to 0 earlier, so I'm not worried about that. And that is how you can find your position function based on the information given. All right, and last but not least, got 2 more problems to do and then we'll call it quits. You have to know your trig antiderivative. So while you learned all 6 trig derivatives earlier in this class back in chapter 2, you have to now know the antiderivatives. So if you look on this chart, while we primarily do sine and cosine a lot of the time, you have to be ready for the rest of them as well. So in this case, if you are given a sine function, its antiderivative is negative cosine. A cosine function's antiderivative is sine, and those are the most popular 2, but these 4, be on the lookout. You never know when they might pop up. Secant squared turns into tangent. Secant tangent turns into secant. Cosecant cotangent turns into negative cosecant, and cosecant squared equals negative cotangent. So the first 2 are the most popular, but the other 4 do show up a lot, especially for those of y'all going on to Calculus 2 next. So we're going to do 2 examples using trig functions, and that will be the end of this material for this class. Example number 5. If the second derivative of the function is sine plus cosine, and f of 0 equals 2 and f prime of 0 equals 5, what is the original function? So first thing I'm going to do is I'm going to find my first derivative because I'm going to do the antiderivative of both terms. The antiderivative of sine, as you can see from the chart, is negative cosine of x, and the antiderivative of cosine from the chart is sine x, but you still got to put your plus c. This time you do have a condition based on the derivative, so let's go ahead and knock that out. F prime of 0 is going to equal negative cosine of 0 plus sine of 0 plus c. Cosine of 0 is 1, so that is negative 1. Sine of 0 is 0, plus c has to equal your condition of 5. Add the 1 over, so c is 6, and you can say that f prime of x is negative cosine of x plus sine of x plus 6. And while I'm going to box it in, that's not your final answer, but that's the first part you have to get right or you will not get the next part right. All right, so now we are going to move over and do our original function, which is f of x. So do the antiderivative of the first derivative. Negative cosine, while it's not on the chart, that's fine. The negative doesn't change, but cosine goes to sine, so this would be negative sine of x. The sine goes to negative cosine. The 6 goes to 6x, and then you've got to solve for another constant that I'm going to call d again. We know that f of 0 is 2, so I can say that f of 0 is going to be negative sine of 0 minus cosine of 0 plus 6 times 0 plus d. Sine of 0 and 6 times 0 go away. Just like the last one, negative cosine of 0 is negative 1, plus the value of d has to equal your value of 2 from the orange box. So adding 1 to both sides says that d has to equal 3, and you can now write your final answer. F of x is going to be negative sine of x minus cosine of x plus 6x plus 3. This is the function based on the information given. And you can double check. If you take 2 derivatives of this, you will get back to sine x plus cosine x as in the original problem.